Hello, good morning, ladies and gentlemen. Welcome to this morning session of National E-colloqium on recent advancement in fluid flow and heat transport 2020, organized by Department of Mathematics, IIT Roorkee. The speaker of this session is Professor Saptarshi Basu, Department of Mechanical Engineering, IISc Bangalore, and I'll request Professor Somnath Roy, IIT Kharagpur, to take over this session. It is over to you, Professor Roy. Professor Roy, is it audible?
Yes.
You can start now.
Okay. Yeah. At the beginning of today's colloquium, first I'd like to thank Professor Naik for organizing such a e-colloquium series over a week, and at this time when due to pandemic, most of our activities and traveling are stopped. Interacting through this medium is being extremely helpful, not only for the students, also for researchers and faculty members. So today we are fortunate that Professor Saptarshi Basu, who is a leading scientist in the area of heat transfer and fluid mechanics and combustion engineering in our country, as well as is an internationally acclaimed researcher, is will be presenting his insights on some of the fundamental issues on multiphase systems. And so Professor Basu is currently DRDO Chair Professor in the Department of Mechanical Engineering at IISc. Professor Basu works primarily on multiphase systems, especially on droplets at multiphase lengths and timescales. His investigations focus around industrial processes like combustion, nanoceramics, etc. Also, his research has answered many fundamental questions which help not only in getting better scientific understanding of the phenomena, but also can be helpful in designing many efficient engineering systems. Institute of Physics, and he is the recipient of DST Sanajanti Fellowship in Engineering. So today's talk will be on multiphase systems and account for transport processes across multiple spatio-temporal scales. I'll invite Professor Basu.
Thank you. Thank you, Shobna, for that rather interesting. Yeah, thank you, Shobna. So what I need to do is that perhaps I need to share my PowerPoint, and so let's see. So can you see my PowerPoint?
Yes, it is visible. Okay. Yeah, crystal clear. Yeah.
Okay. So thanks, Professor, for this particular quite a few well-known and distinguished speakers that you have on the list. I think I know almost all of them.
Your voice is not coming properly, Professor Basu.
Can you hear me properly now?
Yes. You should have to little clear, like close to the speaker.
So what I was saying is that there are quite a few eminent speakers on the list, and I personally know almost all of them in different contexts. So that is good. So let me try and present this talk on multiphase systems, an account of transport processes across multiple spatio-temporal scales. What I'm going to do is that rather than going into the depth of each and every problem statement, and we'll give you some kind of an overview and some interesting results. And obviously, there are quite a few, journal articles and other things that have come out of this. So, if anybody is interested, we can talk offline. Am I audible clearly to everyone?
No, little problem is there. So maybe you can just take the speaker close to your face, I think.
Let me just try to see. Let me change the setting.
Okay, okay, no problem. Yeah.
Just give me a second. Let me just stop sharing for a second. Am I audible now? Am I audible now?
It's
Yes,
better.
yes, bit better. Yeah.
Okay. So this may be actually better. Okay. Let me reshare my screen once again. Okay. Okay. So what am I going to do in this particular context is basically provide a brief overview of some of the interesting problems that we have worked on. And these will be problems at different multiple spatio-temporal scales. And then if somebody is interested, we can talk offline about going into the depth of each and every application. So just to give an idea of the researches that we kind of do. So this is a small cartoon which basically presents the different applications that we work on. So mainly we work on in the area of droplets, which is ranges from droplets at a very small scale, right up to gas turbines, spray dryers, thermal barrier coatings, and so on and so forth. So some of the key phenomena that we try to understand in this particular context is evaporation, atomization, combustion, some interactions of the flow and the droplets, and instabilities. And in cases where the droplets are actually colloidal or particle laden in nature, we also look at the particle transport. So giving this in mind, these are the different application domains. Let us now convert that to an equivalent length scale event. So we work across a large length scale, and that's where the spatio-temporal resolution comes into the picture. At the very large scales, we look at flame vortex interactions and swirl flow dynamics, spray swirl interactions. At certain medium scale, we look at droplet instabilities, droplet atomization and breakup, droplet vortex interactions, and similar such stuff. At a very small scale, where we actually look at interfaces, now we look at functional droplets and how it actually precipitates, how it forms patterns, how about it undergoes boiling, and similar such stuff. So it has a large length scale variation all the way from 1 meter all the way up to 10 microns or so. So these are the active research interest when you put them on a length scale basis. Now, this is a small research kaleidoscope before I go to my actual each and every talk, so that you get the laser pointer in place. So for example, this is what you see over here is basically a swirl flame dynamics. This is basically, these two are the flow field. This is the flame, and this is if you actually have a spray inside that flow field, what happens. So you can see that that the flow field is extremely complicated, and the flame responds to that flow field. And if you inject a spray in such a flow field, the spray also shows some very funny behaviors. So this we can call as swirling flow and flame, and the stability topology and the hydrodynamics. So we are going to spend a little bit of time looking at some of these aspects. Then, of course, the second part is basically, if you look at it over here, you'll find what we call a drop shock interaction. This is a droplet vortex interaction, as you can see, if the videos are running. And you also see certain instabilities when you actually have a droplet, which is, you can see the instabilities over here. So these are, I would say, medium scale events where we look at individual droplets and try to understand what is going on with them. So I'm not going to spend too much time on this, but some of the videos can be quite exciting. And the last part, this is actually goes into the realm of interface. So here you can see these are basically sessile droplets. This, for example, shows the flow field inside a sessile droplet. And this actually shows a certain mixing characteristics in a sessile droplet. And this particular phenomena that you see over here is called a Moses effect, which is basically separation or cleaving a particular drop into two parts in a non-intrusive fashion. So these are some of the things that we can also cover a little bit so that one can understand the different types of works that are going on in the area of multiphase flow. So these will be real small scale phenomena where we actually engineer the interfaces. Okay, so one such example of this phenomena will be, people are familiar with the coffee stain pattern. So how can you modulate the interface so that you can generate patterns of different kinds? So that would be an interesting small scale phenomenon. So let us look at first the large scale phenomena in this particular context, and let us see how we do on that. So the large scale phenomena in which we are kind of intimately involved is basically the gas turbine engines. So as you can see, this is a full-fledged gas turbine, and only that part which is boxed, basically the blue box, that is the box where the combustion processes actually take place. So that is a very small part of the entire gas turbine, basically the driver of this whole system. So if you look at this particular gas turbine, what you will have is that there is a fuel supply that happens, and then there is an air supply. So air and fuel gets mixed, and you get the combustion, a primary combustion zone here, and then you have the secondary zone, and so on and so forth. So as you know, regardless of what we call about solar thermal and other such energies, about 25 to 30% of the world's power is utilized in and in the aviation comes through the gas turbines. So by far, it is the most complicated device in the world. That is why only a few companies actually make gas turbines. And it involves basically liquid fuel at high pressure, and it's a highly turbulent environment. So as you can understand, it's a multi-phase system, which is highly turbulent in nature. And we have billions of dollars that are invested each year. And what people want is basically, you want the gas turbine to operate at all conditions. So it should not go unstable. It should not show blow-offs and extinction events. And the third and the most important point is that the next generation designs, that means we always revise the combustor designs, and the next generation designs and the fuel flexibility, especially the emphasis on bio-derived fuels, we want the combustor to work, as simple as that. So the ultimate holy grail, always it has been, and it is still a holy grail, that's why we call it a holy grail, is basically it's a robust, stable, low emissions liquid fuel combustion system with fuel flexibility. It sounds like a one statement, but it is abnormally complicated for reasons that we are going to see shortly. So why the insights into the gas turbine combustor is required, and this is for a general audience, that you know that because it is one of the major power producer in the world, and as well as used for aviation purposes, you want low emissions and stable operation, as we said, and it can be gas fueled or liquid fueled depending on what kind of a combustor or what kind of a gas turbine you are running. Now to understand, if you look at it, the processes in a very simple way, you inject fuel, say if it is a liquid fuel, it undergoes a process called atomization, in which the fuel is broken up into small droplets. These droplets should undergo a phase change. That means they should evaporate and form a vapor field. This vapor field now should mix with the oxidizer, okay, and ultimately lead to combustion. So now there are several time scales, as you can see, that are involved over here. You have obviously a tau atomization, then you have a tau evaporation, then you have a tau mixing, and then you have a chemical time scale. So all these time scales together actually govern that how good is your combustion. So if your atomization process is not good, what will happen is that it will ultimately affect your mixing. Your mixing will become very non-homogeneous. As a result, your combustion will actually can have
unstable pockets as well as hotspots, which is not good. So the time scales are highly critical in designing the gas turbine combustors. And unfortunately, these time scales are not very easy to control either. So there are people who work on atomization, there are people who work on phase change, and there are people who work on mixing, and then there are people who work on combustion. So all these factors combined ultimately gives rise to what we call a stable combustion. So if we look at it now in a more slightly detailed fashion, what will happen in a combustor? You basically have a swirl airflow, which I already showed. This swirling airflow, as you can see a small snapshot over here, is very complicated because it has got shears, it has got certain unstable modes. Now, when you actually spray liquid or gas fuel to this, there is something called a momentum coupling that takes place. That means the airflow will talk with the fuel. And once the airflow talks with the fuel, you get some kind of a stability dynamics of jets in a combustor. This particular thing ultimately leads to the mixing dynamics and ultimately leads to combustion efficiency. If you have droplets in here, then there are certain things that you need to be very aware of. You get what we call droplet and droplet gas velocity interactions, and identification of dilute versus dense sprays. The droplets can actually coalesce. So there are a whole lot gamut of dynamics that can actually take place. And one such video over here, if I look at it one more time. So if you look at the video over here, you can see that how a spray actually behaves in a highly swirling flow environment. You can see the fluttering from all sides, and the droplets are ejected in a very randomized fashion. So this is what happens when you actually inject a spray in a swirling airflow like what is shown over here. So you can understand the complexity of the dynamics that are associated with this problem. So what we do in order to investigate such a setup, such a phenomena, you basically develop what we call a single can combustor. So you can imagine that there is a swirling flow and an injection in a coaxial manner in a combustor, in a sample combustor. It's not the exact industrial combustor. So as you can see that these are the swirl, and this is the fuel that comes out of it. And then you can have a very high swirl configuration, and from anywhere between 0.4 to 2, very high airflow rates. And we have full optical access, and we can test that how this flows actually interacts with the swirling airflow. So let us look at something which is very interesting now. So in order to see that, as I already told, that for example, in any such combustor, you normally use the swirling flows. And what is a swirling flow? Basically, the swirling flow is that you actually inject a tangential momentum to a predominantly coaxial flow field. As a result of that, what happens is that you get something called a vortex breakdown phenomena. So vortex breakdown phenomena, once this happens, it creates a recirculation pocket very close to the burner lip. So this is exactly how it looks. Now this particular low speed section basically helps you to anchor any flame, because as you know that the flame speed is rather low. So you need a recirculation pocket, and this is done in glove body stabilized flames as well, where the hot combustion products are mixed effectively with the reactants, and you can stabilize them right around the burner lip. So this is how it actually looks like. And this was studied in 1984 by Gupta et al. And then you can read Syred's paper, which gives a good account of how this thing actually goes. So this is what is called a vortex breakdown phenomena, and this is the key. But unfortunately, even though it looks very simplistic, this phenomena is actually very complex. Nobody knows a whole lot about swirling flows as of today. So what we did was that, okay, we found certain interesting what we call hydrodynamic transitions. Now what happens is that if you look at, these are the different swirl numbers, as you can see. So what happens is that this is exactly the flow field that I showed in the previous slide. So what happens is this, as you increase the swirl number in this case, right, as you can see the transition, we get, this is called a pre-vortex breakdown phenomena, where there is a central jet surrounded by a recirculation zone. With the increase in swirl number, that is with the increase in the tangential momentum part of the flow, you get this reduction in this central jet. This is called a vortex breakdown bubble. And then you observe, as you go on increasing the swirl number even further, you get ultimately what we call a central toroidal recirculation zone. So this transition is called primary transition. And this was observed for the first time by our group. Forget about the slightly technical terms about non-orthogonal saddle point and stuff like that. But it essentially shows that the hydrodynamic topology varies quite a bit if you change your swirl number and you change something which is called the Rossby number. So we will come to the Rossby number in a little bit. Rossby number is nothing but a coupling moment that is produced when you actually have a velocity deficit between the two streams of the flow. So apart from this, what also we got is that for actually low Rossby number cases, so as you can see, this is a high Rossby number case. So as you go on increasing the swirl further, so this is from 2 to of the order of 3, you see that there are multiple secondary recirculation zones that are actually formed. However, something very interesting happens as you go on reducing the Rossby number. That means the central jet actually has a very low flow rate. As you go on increasing the swirl now, you get what we call a conical breakdown phenomena. That means the jet basically opens up completely and there is hardly any flow inside the two shear layers that you can see over here. So this is the first detection of conical breakdown that was ever done. Now, this actually illustrates that imagine if you were in a power generation system and your flame actually if your flow actually undergoes this kind of a conical breakdown, then this is a loss of efficiency and an instantaneous extinction event. So this is very, very bad, so to say. And this is a conical breakdown which actually happens in a very small, swirl number space. So why this happens? So as you can see, this is a very simplistic diagram just to showcase what we are talking about. So there is a central jet, there is an annular jet, and then there is a swirling flow, right? So these have got varieties of names, inner shear layer and outer shear layers and stuff like that. So what happens is that if you just have a rotation in this particular flow field, you create a radial pressure gradient due to the rotational influence, and then you have a radial pressure gradient due to the entrainment. Now, as you go on increasing the velocity, the deficit, that means U1 versus U2, that means the central velocity is more. As you go on, as the central the external velocity becomes more than your central velocity, what happens is that this pressure actually becomes more than the outer pressure. As a result of that, the flow undergoes what we call a complete conical breakdown. So this is dominant in the case of low Rossby number cases because the dominance of the swirl component actually leads to the conical breakdown. So, and apart from that, we also have as you add rotation in the vortex core, it also leads to something called centrifugal instabilities that I have not shown over here. It is there in the papers that we published in this particular area. So now all these scientific contributions are great, but ultimately what you need to give to the industry people is that they need something like a regime or a topology map. So you cannot really just say that, okay, these are different bifurcation phenomena. There are a lot of things that are going on. They would really want to see that whether it is usable or not. So this is exactly what has been done. So in terms of swirl number and Rossby number space, we have designated the different regimes. For example, regime 1, as you can say, it is a pre-breakdown dual rings. Then regime 2 is the first occurrence of the bubble mode. So these are different instances. Okay, and these are fictitious lines, which basically designates the pathways. For example, for a particular Rossby number, if you go on increasing the swirl number, you will go from 1 to 2B, which is basically in this particular section, and then you go on to 3. 3 is the supercritical flow states. Similarly, it depends on where you start from, and as you traverse, you are going to traverse different flow states, or basically different topologies in the different sections, depending on where what the swirl number and the Rossby number is. So this is particularly exceptionally useful for the industries, because then they actually know the two operating parameters, and therefore they can find out that how your flow behaves as you go from one point to another, right? So if you do not want, say, stage number 4, which is basically an open bubble, okay, then you should avoid this green colored space. That means you should operate at a slightly higher Rossby number, and then you can go on increasing the swirl number without ever entering into this stage 4. So these are certain very interesting characteristics that we found, and this has been put to good use in a topology or a transition map. So is that all? Because you see that this is nice in the sense that these were all what we call time averaged dynamics. If you now look at the flow fields, and if you take the high speed data out of it, so this is Rossby number greater than 1 and Rossby number less than 1, and if you deconstruct the flow field, you can actually find out the different modes. So this is basically a proper orthogonal decomposition of the different modes. So you can see, for example, mode M1 designates strong shear and circulation. Mode 2 actually designates shedding. Mode 3 actually designates strong shedding, and M4 designates what we call the helical shear. You can see from how the patches are organized. You can see this. So you can see that in the case of a pre-vortex breakdown bubble, you get high. If you just cast it now in a frequency map, the different modes, you will find that there is a presence of a very strong shear mode, and then there is a presence of a very strong shedding mode at two different frequencies. One is under 50 hertz, and the other is close to about 90 or 100 hertz. So these modes are particularly important because they can later on also couple with the acoustics of the combustor, which are all in this particular range. So on the other hand, when you actually deconstruct the CTRZ, you don't get the shedding mode that much. It is kind of suppressed. So these informations can be only provided when you actually do a high-speed realization of the flow field, which is not there, as you saw in the previous slides. It's not there on the time-averaged flow fields. So as the key points over here, you can see a strong shedding mode in pre-vortex breakdown bubble, but the shear is more dominant in the case of a CTRC. So the shear mode is very dominant. And this is how the energy, so these modes have been arranged in terms of the energy that they carries. So therefore, M1 should carry the maximum energy, followed by M2, and then M3 and M4. 4 modes normally carry more than 95% of the total energy that is present in a particular flow field. Can we use this now in the hydrodynamics in the case of a flame topology? Because you can argue these are all hydrodynamic transitions, which is nice and good. But what about when you actually have a flame which is sitting on this zone? Because that is what you want. So similarly, as we showed, we came up with a regime map in which the swirl number and the Reynolds number have been plotted. Now, as you can see, once again, B2 and B1 designates the two flame blowout and blow-off incidents. Okay, so blowout and blow-off are slightly different things. Blowout happens when you have excessive swirl, so the flame actually gets quenched, whereas blow-off happens when you have excessive coaxial flow, no swirl in this particular case. So the flame basically blows off because there is nothing to hold it. So, so in between, of course, you have different flames. For example, you have swirling seated flames, you have lifted blue flames, you have stretched coaxial jet flames, depending on what is your swirl number and your Reynolds number. And these are the different pathways that they are followed. Once again, when you go from path, for example, this particular path, path 1, you see that there are certain, or path 2, you see that there are certain transitions that the flame undergoes. And these transitions, okay, are very similar to the hydrodynamic transitions that you see. So the burner is the same, everything is the same. So these transitions actually tell you that how the flame behaves in conjunction with the flow field. So the dynamics in general depends on the vortex breakdown bubble. That is the key component of a swirl flow around which it is stabilized. So I'm not going to go into the stability mechanism per se. It is very similar to what we had earlier. So, so let me look at some of the flame dynamics, because this is something that is very visual and something very appealing. So as you can see over here, this is the entire life story of a flame. So for example, we start with very low swirl number, that is 0. You get the flame, which is basically a stretched jet flame. As you go on increasing the swirl, you get a flame which is a little lifted, and it is anchored on the wake of the recirculation zone. So this is the flame images which has been superposed on the flow images to give a better understanding. As you go on increasing the swirl number, as you can see, at a certain swirl number, the flame gets seated on the burner lip, and it actually encompasses the recirculation bubble, exactly how you want it to be. And then as you go on increasing the swirl number, the flame actually stretches, like with the flow. Ultimately, what happens if you go on increasing the swirl number even further, what happens, you get a conical tailpiece of the flame. This conical tailpiece expands, the recirculation gets actually diminished. And at certain point, when the swirl number is very high, of the order of 7 and 8, you have excessive strain on the flame, and the flame undergoes an extinction event. So these are basically the time history on a time average basis. You can look at one particular box over here, and you can also look at the time series. These are high-speed chemiluminescence images, which basically shows the twisting of the tailpiece, right? So, and similar thing you can see for the high swirl momentum case, where you can see that the flame is rather short, and it is almost to the point of extinction. So this is a very narrow, it's a very short flame that you can actually create. So this is the time history of the flame, which is rather interesting. And this actually tells you that how the flame topology should change and how their dynamics should change depending on the hydrodynamics of the flow field. So this is what actually should happen in a gas turbine combustor also. Now let us spend a little bit of time looking at the dynamics of the fuel spread. So this was all gas phase that we considered. So it was very nice, and because it was all gas dynamics, so there was not much to, not much of a complexity except for the fluid dynamics part of it. But however, when you actually put liquid sprays into this, as I said earlier, there is an evaporation term which you have to bring into the picture. And then there, of course, is the atomization process itself. So evaporation and mixing and atomization are the key parameters that comes into the mix. And all these things should be less than the residence time in the combustor for you to achieve good quality combustion. So, but the droplet size depends on a lot of things. It depends on the spray nozzle, and it depends on the interaction and a lot of other whole lot of parameters. So let us see a few of them in a little bit more details. So I'm going to skip this slide. So as you can see that there are a lot of complicated dynamics. This is a rendering by Sanchez from UCSD, who actually showed that, okay, if you have a flow that is coming out, it will actually undergo what we call fragmentation. And these liquid droplets now can either migrate towards the high shear region and not stay within the strongly vertical region. And there are multitude of studies in this particular section. And how these droplets actually evaporate and give rise to group combustion behavior is a hot topic as of today. So there has been numerous papers, numerous people who are actually working on this phenomenon. So we tried to look at one such thing in a little bit more details, actually several things. I'm going to just present one. So what happens is that if you look at this particular flow field, so as you can see that we already stated earlier, if you fix the burner geometry somehow, that means if your blade angles are fixed, then as you go on increasing the flow, we already spoke about that if you just increase the flow rate, what will happen is that you get certain unstable modes that are normally present in the flow field. In this case, it is the Kelvin-Helmholtz mode, which is basically mode A1. And then there are, of course, helical modes and the shedding modes. And some of these things are shown over here. I don't know why this did not play. It did not play. This is supposed to play. Okay. In any case, so what happens is that if you look at now the flow field in several pieces, you will find that then there is a zone A and zone B, and then there is an inner shear layer which separates the vortex breakdown bubble from the shear, that is designated as this red line. and then there is this outer shear layer, which is designated by this line, which basically separates the flow with the ambient. So as you can see that there are quite a couple of shear layers, and then there is a strong vortex breakdown bubble. So as you can see that depending on, it can be a strongly recirculating flow or it can be a weakly recirculating flow, depending on what swirl number you are using. So if you look at now the transitions over here, let me see if this video plays somehow. So, as you can see, this is only the spray. So this is taken as there is no external flow field, if you can see the video. So this is just a nominal flow field. Okay, this is how the spray should normally look like. This is a spray where you actually have a lot of interactions that is going on. As you can see, the fluttering of the spray. So this is this is weak interaction. This is spray with swirl. And now you have a strong interaction, as you can see, the flow is doing the dancing. It's basically a flapping, very strong flapping of the flow field. So there are certain mathematical calculations that you can show, and you can say that, okay, what is the degree of coupling? So this is a little mathematical. I'm not going to go into the details of this, but what I'm going to show is what we did, interestingly, and this should be a major takeaway point, is basically we found out that how the spray itself, we did a proper orthogonal decomposition of the spray. So S1, S2, S3, S4 designates the modes of the spray, where A1, A2, A3, A4 designates the modal decomposition of the flow. So now what happens is that when you now plot these modal frequencies with something called momentum ratio is the ratio of the flow of the liquid fuel and the gas fuel. So it is a ratio of the two. So as you know, the gas flow will be always more than a liquid flow. So as a result of that, momentum ratio is always greater than 1. And higher the momentum ratio means you are pumping more air into the flow. So what happens over here is if you look at the modal frequency space, you will find that when the momentum ratio is below 300, okay, the modal frequencies of the flow and the spray are not aligned with each other. That means they are not the same. However, as you go on increasing the momentum ratio beyond a certain point, which we call the critical or the transition zone, all the frequencies actually merge right on the top of each other. So therefore, if we call this region to be the weak interacting flow, that means the MR less than MRC, you will find that the liquid phase is almost oblivious that there is a gas flow at all associated with it. So its gas dynamic, its transitions and its dynamics or its evolution is normally insensitive to the gas flow field. But moment you go to high momentum ratio, you get a very strong coupling effect, and the gas and the liquid flow field actually starts to mimic the gas flow field. So the oscillations in the liquid sheet scales with the Kelvin-Helmholtz frequencies. So if you can see, so what happens is this, the gas phase and the liquid phase gets locked with each other with the Kelvin-Helmholtz mode at that particular mode, and they start basically to dance to the tune of the flow field. So beyond a certain momentum ratio, it is the gas flow field which basically dominates the liquid phase. So that is that important takeaway message over here, as you can see in that particular region. Now, of course, normally one other thing that we try to actively look at, you see the breakup dynamics. If somebody has studied breakup, they will find that in breakup, it is always the linear velocity that is taken into consideration. That means you propose a Weber number, and in the Weber number, you have a flow velocity, and you have some kind of a length scale parameter. Now, the normal length scale parameter will be the droplet size or the sheet thickness, etc. And the velocity will be normally the linear velocity between, or the linear velocity deficit between the gas phase and the liquid phase. This is how all the breakup dynamics have been constructed. However, there is a catch over here, because this particular flow field has got such a strong vertical shading component. We argued that we should have a Weber number which is defined on the circulation strength. So if you look at it over here, this is the Weber number, which is based on the circulation strength and the sheet thickness. So either the circulation strength, or you define Weber number based on a boundary layer thickness, which is basically the vorticity boundary layer thickness. So this is the diffusive thickness of the vorticity layer. So these two parameters should be the parameters which should give you an idea of the flow field. Because if you just use the linear velocity scale in these particular cases, what will happen is that your Weber number and your breakup modes are not going to match each other. So, and this makes far more logical sense. That is because in the shear layers, as you saw those flapping, there's a very strong vertical component of the flow field, and it is the vortex which basically stretches the sheet and basically strips it apart. So, this was one of the definition of the Weber number that we proposed. And based on this, what we can see is that basically for momentum ratio equal to 0, you have a nice axisymmetric breakup. When momentum ratio is equal to MRC, you have an extension of the sheet, and then you have this strong recirculation which leads to that extension of the liquid sheet. As a result of that, you get a strong centrifugal instability. And when your MR is much greater than MRC, that means you have a very strong momentum ratio. That means the gas phase is really, really dominant. You get a lot of flapping. So this is due to the circulation, as you can very clearly see. And the flapping frequency, as we showed earlier, matches with the Kelvin-Helmholtz mode. And because of the very high Weber number, this region has got significant importance in generating the low droplet sizes. So this is the most important parameter that you can think about. Okay, and most of the gas turbine combustors will work in the MR greater than MRC space. Can we now use it in the case of a non-dimensional map? Oh yes, we can. So you have a Weber number. This is again, note the definition. This is a revised definition of Weber number with the momentum ratio space. And this Weber number has been defined with respect to the vorticity layer thickness. You can also define it with circulation thickness, no problem. As you can see now in this Weber number space, this is also an industrially relevant map. You can choose your Weber number and you can choose your momentum ratio. One can predict what kind of a modal breakup you are going to have. So is it in the strong interaction region? Is it in the transition zone? Or is it in the axisymmetric region? So you can see using this kind of a map, which goes up quite a bit, you can actually predict that what kind of breakup that the liquid spray is going to face. So if you put it now in a nice little map, you will find that if MR is greater than MRC, you have an amplification of the Kelvin-Helmholtz wave, coupling of the momentum transfer, and then you have primary ligament and droplet formation. If you don't have that, you have long wavelength KH waves actually dampens, the surface tension actually dominates the breakup, and you get certain droplet sizes. So this kind of a mechanistic understanding of the flow field was important in a swirling environment because such a literature is quite shallow. We don't have much of a work in this particular area. And this is particularly relevant, as I said, to the gas turbine ultimate combustion process, because the droplets that you generate ultimately determines how good is your mixing and how good is your combustion. So from this part, this is all large scale. This is one snippet. Of course, there are a lot of work that we have done on this droplet vortex and other type of interactions. I'm going to switch gear and just show you an entirely different scale, because that is the title of the talk. It's a journey through different scales. We are going to show now a completely different situation where there is no turbulence. It is an interfacial phenomena. And let us try to see what are the cool physical outcomes that we see in the next 15 minutes or so. And let us see how we can now translate this small scale phenomena and take it to different applications, including the current COVID pandemic. Let us see that whether we can do something about that also or not. So this is a snapshot of certain real world applications. And let me take a minute for this. When you actually have a droplet, now forget about sprays, high speed flows. Now we are into the very low Reynolds number regime. Okay. So mostly diffusion governed, but of course there is a little bit of a flow also. So this is a droplet, for example, which is sitting on a platform, and this is another droplet which is sitting on the same platform. One is hydrophilic and one is hydrophobic. Now, as you can see, depending on whether it is hydrophilic or hydrophobic, okay, if these droplets contains particles, you will have different patterns of deposits that are left. Try this with a coffee drop on your table. If you dry that coffee drop, you will find that there is something called a ring-like precipitate that is left on the surface. So that happens due to a particular flow phenomena, which is called capillary flows, which gives rise to those kind of surface pattern. Whereas on the other hand, if you have a hydrophobic droplet on the other side, okay, the flow pattern is slightly different and you get different types of deposits. Now, these forms a template of different self-assembly assembly context in the case of multiphase physics. So these, what are the governing processes? Governing processes, of course, range across multiple scales. For example, evaporation dynamics is strictly a milliscale phenomena. The flow that is created is microscale, and if it is a particle-laden droplet, especially nanocolloids, you get self-assembly, which happens at the nanoscale. And depending on what the governing processes are, your morphodynamics of the precipitate, that means what the precipitate actually looks like, can have different structures. Like, for example, in the nanoscale, it can have an order to disorder transition. In the microscale, you can get these buckled shells, which is again a solid mechanics phenomena. So in this droplet, which are roughly of the under millimeter in size, you get a whole gamut of physics that you normally would not associate with this small scale. Okay. And what are the real world applications of this? You can develop photonic crystals. You can have mixing at the small scale. I think there was a talk by Professor Shuman Chakravarti earlier. So as you know from his talk probably, that microfluidic application requires mixing at the small scale, and it is very, very hard because there is no convective effect. So can these, dynamics of these droplets or the interfaces can be tailored so that mixing at the small scale can be enhanced? Then, of course, you have 3D printing, which is a big ticket item these days and ranges across multiple applications. You have medical diagnostics. And of course, you have the problem of surface patterning. These days, you have sensors and actuators which are actually printed on the surface. So all those things will have a droplet framework. And in the droplet framework, there will be different ways by which you can actually modulate the droplet. So it is still droplet, except that the flow physics is very different. So let us look at some of this flow physics. So at the center, you always have a droplet. Now, what happens is that when you actually heat the substrate, okay, you have something called thermal agitation. This can actually lead to certain shape characteristics of the droplet, which is something which is very interesting. And then if you have mechanical agitation on the surface, basically you oscillate the surface. What you do is that it leads to certain vertical flows within the droplet because of mean streaming. And as a result of that, you get different surface patterns. Okay, so this is what we call mechanical agitation. Then the part that I'm going to talk about, which we'll find interesting, is basically what we call vapor-mediated interaction. That means I'm not going to touch the droplet, but I am going to change the governing physics of the droplet in such a way that we achieve certain goals. And similarly, there will be other things like chemical tailoring and variable weightability, which is basically modulating the surface in such a way that it is a case of interfacial reengineering, so that we can develop patterns of our choice. So we are going to look at vapor-mediated interactions in a little bit more details. So without spending too much time, as you can see, droplets never come alone, right? So even from spray drying applications to 3D printing, it is always multiple droplets which are situated close to each other. So can vapor-mediated interactions between droplets significantly affect the evaporation dynamics and the topology of the precipitates? So this is the $1,000 question that one needs to answer. So what happens in the case of vapor mediation? Okay. So vapor-mediated reactions, what we will have is that you have a certain array of droplets, say for example, right? So these are droplets which are sitting nice and close to each other, separated by certain distances. Now, if you look at the center droplets, they are basically always the same. So it is only a center droplet which is flanked by two side droplets always, right? and there is a length scale separation of L1 and L2. This L1 can be equal to L2, it can be different from L2. So what happens is that, what happens to the physics? So normally if we have an isolated droplet, in these cases, in the absence of flow, it will actually undergo a diffusive mass transfer. And as a result of that, it will shrink in size and stuff like that. But there is no convective effect as such. However, on the other hand, what we have is that when you have two droplets side by side, what happens is this. If you look at this droplet very carefully, what does it see? It sees a neighbor on both sides. So when these droplets actually evaporate, these regions, which has been marked in red, has got a vapor-rich regions. That means it is, for example, if these are water droplets, so these regions will have a higher relative humidity, so to say. That means it will have a higher concentration of the vapor. Moment it has that, it has a higher concentration of the vapor, what will happen? The evaporation from these sides will be reduced. Because if you look at a diffusive transport, what will happen? Diffusive transport actually is dependent on what is the local concentration of the water vapor or whatever fluid that you are actually drying. So there is a suppression of evaporation on these sides, but these sides should continuously show its normal evaporation. So if we designate this area as something like this, okay, so ADI is the droplet surface area, and this is the vapor front area. What you will have is that we can actually merge all of these into a universal time scale. And this is a JFM article in 2019 that we published, where we showed that any droplet of this particular configuration on any substrates, glass, PDMS, whatever that you are, silicon that you are going to deal with, they can be all universally represented by a single criteria, which is this, essentially this, and they all merge. That means, let me tell you that what is the implication of this. The implication of this is that no matter what substrate you give me, no matter what fluid you give me, I can predict that what will be the total evaporation time. And that is a significant step, because in this entire array of droplets, you are taking the collective evaporation into consideration, and you are coining a universal time scale for the same. So the math is something that we can discuss later. Now, the flow field actually shows something which is even more interesting, and that actually has a very strong effect on the particle transport. So what happens is that if it's a single droplet, the flow is like this. Okay, this is micro PIV images. When you actually have a side droplet, what happens is that on this side, the evaporation is suppressed. So naturally, evaporation happens more on this side. So naturally, the flow is driven towards the side where the evaporation is the most. Now you have the center droplet, which is flagged by two side droplets, as you can see from both sides. Here you can see that the flow normally shows that's this very weird pattern. That is because evaporation is suppressed on two sides. So naturally, the flow is going to converge on these two, right? And because it is symmetric, it shows that very nice symmetric distribution. Okay. So this was a very interesting flow physics apart from the universal merging of the time scales. Can we now take it to a two-dimensional droplet array? So this is a two-dimensional droplet array. So that was a single dimension. Now here also we can do the same thing, but here we do something called a Voronoi tessellation of the whole arrangement. And what happens is that this area that is there, this AV, is basically the vapor front area, right? So it is the equivalent of the area of that vapor front that we showed in the case of a single array. Once again, once you can do the same math and you can show that for a hydrophilic class of droplets and for a hydrophobic class of droplets, they can be all merged under one equation. Okay, so this particular thing shows that whenever, and this was published in PRE this year, actually, early this year. So it actually shows that, okay, regardless of the extent of confinement, if we know the geometrical factors and if we know the confinement arrangement, we can predict you what will be the time scale of evaporation in the case of these confined droplets. Okay, so it always scales as a function of this. So that was rather interesting. Now we thought that, okay, now that we have done it in different droplets in different arrays and different configurations, why not take it and put it in a microfluidic or a milli-channel configuration, because that would be very critical in the case of if you want to do this biomedical diagnostics, say for example, within a channel. Can we actually somehow predict how the droplet is going to dry using a very similar principle? So this is what a droplet in a confined channel looks like. Okay, very similar arrangement, except the vapor field looks like this. So what happens is that indeed, if we do the same scaling argument, okay, you indeed see that again, you can merge the droplet based on the geometry of the confinement only, and there is indeed a universal time scale. So you can actually extend the droplet lifetime to 8 times depending on the region of high confinement. That means if you narrow this channel and make it very long, what will happen, that is, this is the length of the channel. So as you go on increasing the length of the channel, your evaporation will come down. If you go on decreasing the width and the height of the channel, that means you make the channel smaller and smaller, your evaporation time is going to skyrocket. So this is indeed a universal time scale. And then there is no limit on this so long as your droplet does not touch the channel wall. So that was rather good. And we also studied the flow physics in this particular droplet. It is a little bit more complicated, but in essence, you can see that the flow basically follows the two regions. It shows the same pattern. Basically, the open end of the channels are where the evaporation will be happening. As a result, the flow will actually proceed towards those regions. So this is exactly what we see, the asymmetric nature of the flow field. And indeed, there exists a universal time scale across all confinements. So that was very heartening to know. Now, can we take this framework now and do something with the surface patterning, right? So what happens when there are nanocolloids in the droplets? So as we have already seen over here, that when it is a single droplet, what happens is that the colloids will nicely get deposited in this particular fashion. It will form what we call a shell, a nanoporous shell, which has got the thinnest thickness at the top. This particular spot actually undergoes what we call a buckling phenomena, a micro buckling phenomena, and you will see what happens over there. So on the other hand, if you have a paired droplet now, we have already shown that the flow goes to the other side. So naturally the flow is something like this instead of that. What happens is that the deposits are more on that side and less on this side. As a result of that, the weak spot hasn't got an angle and it buckles from the side. So it will be always side buckling towards the side where the other droplet is. Do we see that in reality? Indeed, that is what we see. This is a single droplet which just buckles. Okay. And this is a paired droplet which actually shows an angled buckling, as you can see over here. So this is what we call the talking droplets. So this all happens because of the flow, and the arrangement is drastically different depending on what kind of a confinement you have. So these are two droplets just speaking to each other side by side. Okay, and this is of course can be translated to any number of droplets in the array. So that was good. Now let us see that if you now put now the entire problem of any mixing of any droplets is, for example, if this is a blood droplet which contains a reagent, the flow due to diffusion is so slow that it basically kills everything. Okay, the flow is of the order of 10 microns per second. On the other hand, you can see that if I put, for example, an ethanol droplet beside a water droplet, what happens is that the vapor from the ethanol gets asymmetrically absorbed on the water surface. It is more on this side and less on this side. It creates a surface tension gradient. You get an augmentation in the flow field, which you can see from this very strong rotation. This is of the order of millimeter per second, 10 millimeter per second. For a single droplet, this is a huge flow rate. And this actually can enhance mixing and reagent reaction by quite a bit. So that is a whopping 10,000, 1,000 times increase in the flow velocity. So we have not done anything other than putting an ethanol droplet to the side. So this is completely vapor mediated. Okay. And that is, you can translate the same thing to a colloid solution also, and you can control what kind of a shape you are supposed to get. So this is also shows that this is the mixing characteristics. If you watch this video, right-hand side is a diffusive droplet. And here, as you can see, it instantaneously mixes, whereas the slow mixing due to evaporation hardly goes on, right? So it is very slow process in itself, right? So if you do an intensity mapping, the mixing time increases by an order at least, even in a viscous flow like glycerol. So you see that just by doing vapor-mediated interactions, we can actually change the flow field and the mixing in the droplet by quite a few margins. And this is completely in situ and completely contact-free. We took the same thing and did something on the splitting of droplets. So in some cases, you have to split droplets. So when you actually bring an ethanol, similar ethanol near a droplet, as you can see, it just basically, this is the ethanol droplet, which is non-contact once again with respect to the pure water droplet. It basically cleaves the droplet into two parts. So that's why we call it the Moses effect, because of Moses' splitting of the Red Sea. So this is what exactly happens, right? So you split the droplet into two parts. And if it contains particles, you can tailor the deposit of the particles as per the way that you want to split the droplet. So this has got very good implications in varieties of applications. Now, I am going to show something before I end the talk. Two things that I wanted to show. One thing is that all these droplets and other things that we did, can it be now used in the case of COVID-19? Now, I would just give a 1 minute, 1 minute kind of thing that what the COVID, how the COVID spreads. So when a person actually sneezes or coughs, what happens is that he ejects a few thousands of droplets. The droplets which are large basically settles on the ground and forms what we call fomites. This is why we clean our Amazon packages and our vegetables and our bags, etc. Some droplets which are small enough, they remain suspended in air. Now, the droplets that are ejected from our mouth basically contain salt. So ultimately, at one point of time, this will become crystallized in air. So this floats in air for a significantly longer period. And what happens is that this can cause infection due to respiratory mode, and this can cause infection due to touch. Okay, so you can read the paper in Physics of Fluid very recently where we analyze these modes. Now, can it be useful in COVID? So what happens is that nobody has seen this earlier. So what we did is that we acoustically levitated a respiratory fluid droplet, that is the droplet that comes out of our mouth. We actually watched the drying phenomena of such a droplet till the crystallization phase. So these are crystals. Okay, we matched it with our 1D model. So this is basically kind of like a D-square model. Okay, and then what we did is that we did what we cleverly, we added virus-like particles. Basically, these are fluorescent particles inside the levitated droplet at the same viral loading. And what we see in the crystal is you can see this lighted up crystals. If you can see it, the lighted up crystals over here, as you can see, these crystals actually show that all the viral loads is embedded within the crystal. Okay, so that means is that when ultimate desiccation actually happens, all the viruses are self-contained within a crystal blob. And this crystal size is roughly 20% of the size of the initial droplet from which it is created. So this levitated droplet gave us a wonderful feel that how the viral loads are distributed in an aerosol. So that can answer a lot of questions that how the virus actually spreads. Similarly, we did the same thing of sessile droplets, that is droplet on ground. That means the fomites that we talked about a little earlier. So here also we see that when it, and this is done on ceramic, glass, plastic, and steel, and these are basically the virus or the virus-like particles. You will find that when a droplet dries, most of the viral loads are therefore at the edge. Very little viral load is at the center. So if you manage to touch an Amazon package, don't touch the edge. That would be the take-home message for this. And I want to end this talk with a nice little video, which on a recent work that we did on droplet impact on face masks. That means the mask that you wear for the purposes of, going out. Now we use masks of all kind. At least in Kolkata, people also use, handkerchiefs around their faces. And in many other cases, I've seen people use handkerchiefs. What happens when you actually cough, when you actually have the face mask on? Is it kind of beneficial? We'll just have a small video, which is a couple of minutes in length. which actually will show that what really happens when you actually cough while wearing a face mask, which is of inappropriate quality. So let's take a look at that, and probably this can be a take-home message for everyone. Okay, so let's look at this particular video. So I'll go to the this comes with a little bit of music, but okay, right. So just enjoy it. This is the most important part. So as you can see, just as I end my talk, that when you use a mask, please go ahead and use a triple layer mask, because if you use a single layer mask, what you are actually doing is that your cough droplet undergoes secondary atomization and it can become aerosolized. And as a result of that, what can happen is that you will have more infectious droplets in your vicinity, therefore causing more damage. So this is something to look forward to. And therefore, one should use a mask, and therefore one should use a triple layer mask. That is the thing. And this is a nice little video, which is currently under review in a journal. So with this, I kind of end my presentation. Okay, there are a lot of things more to be covered, a lot of things that I did not cover. So I would be ready. Shomnath, I don't know what is the protocol after this. I'll stop sharing the screen.
Yeah, yes. Thank you, Saptarshida. It was a very nice talk, and I was currently kind of sticked in front of my computer screen. I thought of doing something else during this period, but I couldn't go out. So from the audience, if there are a few questions, because we have substantial time for question answer. So,
yeah, Professor, Professor Roy, this is Arup here from Roorkee.
Hi, Arup. Yeah.
So I don't have any question. I have a comment actually to Professor Basu.
Yeah.
So yesterday we have actually listened to Professor James Feng. So in his lecture, everywhere we have seen the bubbles, lots of bubbles, cluster of bubbles. So eventually, I was thinking to give him some sort of tag as bubble man. So today, Professor Basu has actually talked about droplets. So Professor Basu can be called as droplet man. Okay, so this is a little small comment. Anyhow, nice lecture. Thank you, Professor Basu, for
Thank
attending
you.
this one. Thank you.
Thank you. Thank you so much, Arup. Thank you.
Thank you.
Yes, from audience, questions or comments.
Professor Roy, can I ask a question?
Please go ahead.
Professor Vasu, this is Manoranjan Mishra from IIT Ropar.
Hi.
It was very interesting and nice presentation with so many information. Could you please give us some information how the absorption you are mentioning about the ethanol and water, that
Right.
ethanol vaporized and get absorbed with the water droplet. The absorption helps mixing.
Yes.
So can you?
Sure. So what happens is that where you have to place the ethanol asymmetrically, because if it is for example, if you put the same droplet in an ethanol vapor field, which is homogeneous, what will happen is that the ethanol vapor will get absorbed on the water surface, okay, and everywhere the surface tension will be lower. So you will have the droplet which will spread a little bit. What happens in this particular case is that because if you just solve a simple diffusion equation, you will find that the ethanol concentration on the left side or the right side of the droplet will be more than on the left side. As a result of that, the adsorption amount will vary, because if you look at the Langmuir adsorption, isothermal, stuff like that. So what happens is that this slight surface tension gradient, okay, is responsible for a very strong Marangoni flow. And Marangoni flow, if you just create this very small surface tension deficit, okay, and if you continuously maintain the ethanol on that particular side, you will find that this flow now becomes of the order of several millimeters, right from 10 microns, because 10 microns is the flow scale that you get, that is a normal capillary flow. That means because there is a non-uniform vaporization, you get a small flow field that is created inside the droplet. So that was the whole idea. Now, it need not be ethanol. It can be any two species which basically absorb each other. But the key is to basically have an asymmetric distribution. And you can also control the footprint of the asymmetric distribution also. That means your footprint of the ethanol vapor. Okay. And so you can control it over a certain range of operation.
So how do you measure the mixing? Because you take the concentration gradient.
So we actually, I didn't show, we calculate the concentration gradient. Okay, both numerically also you can do it, because it's a diffusion problem, and you can actually have an adsorption kinetics on the surface. We have also done what with the concentration measurement. We have also done not with ethanol but with acetone, because acetone actually has a LIF signature. It's a laser-induced fluorescence signature. So we have done that and see that how this concentration actually, whether it is really there is a variation or not. So both of those two things we validated, and then we came up with the actual surface tension gradient, the actual deficit in surface tension, and then you use it to calculate the Marangoni scale. So the Marangoni scale is just a scale. It is not an exact value. The exact value comes, of course, from the measurements.
So but there will be no instability phenomena. It will be.
We did not see that. You are right, but okay. If you are right, because normally we did not see. But when you have actually particle-laden droplets, that means these droplets now have particles. Okay, we see certain funny things also. That means the flow slowly, because as you change now the density of the medium, right? It actually affects the flow in a different way. So currently that is a work in progress. So, but normal droplets, if you just talk about mixing, we did not see much of an instability as such.
Thank you very much.
Okay, anybody else from the audience?
Hello, Professor Boshu. This is Amir. Yeah, yeah. I have seen your paper actually. This COVID
Yeah.
paper in physics of fluid. So you have used a lot of mathematics there also. So
Correct.
yeah, can you give me a little overview of this mathematics, whatever you have used there?
Yeah. So the COVID paper that we did, okay, and okay. So that was what we. It is not just me and my colleagues. I mean, my collaborators, Professor Shetoprabhu Chaudhary and Professor Abhishek Shah. Abhishek Shah was my own PhD student at one point. So what we decided to do at that particular point, if you look at all the epidemiological models that are currently available, and I might sound a little rude, but most of them would be some sort of curve fit, or they will be agent-based modeling where you don't have an handle of the actual physics of the problem per se. So you will have certain what we call unconventional or ad hoc constants and functional forms. So what we decided is that we wanted to look at that when you actually eject a droplet from the mouth, right? This is a droplet, how this droplet actually is linked to a pandemic situation. Okay. So what we thought is that we know a lot about droplets. So as the droplet comes out of the mouth, we modeled it as if it's a droplet which is coming out in a puff and a jet. Because when you cough, what happens is that if you can visualize a cough, you will find that initially it's a puff, initially it's a jet, and then it transitions into a puff. Okay, so it's almost like as you spray your your sanitizer in the room. It's almost like that, of course, at a lower velocity. So what happens is that this droplet actually now is cocooned inside this puff and jet, and it undergoes evaporation and crystallization, both of which we were able to model. And then what we did is that after we found out what are the time scales that comes out of it, then we did another interesting thing. We thought among ourselves that that we have a lot of experience in combustion and stuff like that. Why not use the combustion chemical kinetics framework, okay, and cast this pandemic into a chemical kinetics mode? That means here it is almost like a person coughs and then another person comes into the vicinity. It's almost like two molecules colliding with each other in a chemical kinetics parlance. So we converted that to a chemical kinetics model, and one of the parameters of the chemical kinetics model was this droplet lifetime. So we established what we call a connection, and it's a physics-based connection, right? Because that was validated data. With this droplet lifetime was connected to how the pandemic can actually spread. And that was what the physics of fluid paper was all about. It connected the two things. We took a chemical kinetics part, we took a droplet physics and merged them. So that was exactly how it was done. So we solved basically a chemical kinetics problem. It's a reaction kinetics, like 3-equation model. And we did a 1D, evaporation crystallization model and coupled it. So that was how it was done.
So a lot of analytical and numerical results also you have presented there. So analytical skills, can you little
analytical skills was that, at that point of time, interestingly, there were no students around. So it was just the three of us, 3 faculties sitting in 3 different countries. Me in IISc, Abhishek was in UCSD, and Shetoprabhu is in Toronto. So Canada, USA, and India, right? So we did not have anybody to work on, basically. So, and the labs were closed. Okay, so I did some experiments in my own office. And then what happened is that we did the modeling ourselves. We used MATLAB. Like the coding was done. Okay, by the way, the coding is kind of pretty simplistic, as you can see, because the kinetics was solved by a simple eigenvalue. So it was a simple eigenvalue problem, and this droplet framework was solved by a simple 1D. It was an ODE, so we used the MATLAB ODE solver. So we solved it. We merged the crystallization model was also another ODE, which was coupled at the later stage. So all these things were done in-house, okay, by the 3 of us. So mathematically, it was not a Herculean task. Okay. Now, of course, we are doing it because we are now shifting to a 3D model of the droplet. And that now requires, I think if Sriporna is there somewhere in the, I think I saw her somewhere in the list. So she was actually doing the 3D modeling of the droplet. That, of course, is a full-fledged CFD endeavor, which involved basically the discretization of the energy, that is the energy and the species balance equations, and Sriparna did it with Frank Nicholson, I believe, right? So so now, of course, it becomes a
Professor Basu,
yeah.
so
Please.
Professor Basu, this is actually triangular attack to a spherical drop. What you, Professor Shwetoprabhu,
Yes.
and
Yes.
Abhishek have done. So that is a
Yes.
triangular attack on a spherical drop.
Yes.
On a lighter note.
Yes. And after a long time, we did some coding on our own, which was very satisfying. Okay, so, and it is end to end. That means end to end. Almost no student was involved. Okay, so
Okay.
you all just checked it.
Okay. Thank you.
Anybody else from the audience? Okay, hello. Yeah. Before somebody else asks, I have a question. Which is not from the hottest topic of today's discussion, COVID, but from the hydrodynamic instability and flame propagation part. And this is very interesting, that how, when you are showing how hydrodynamic instability modes are changing the flame shapes and the flame propagation. But is there, in the same way, is there any mathematical? There must be mathematical correlation between them, and if you can discuss on that. And also, these different hydrodynamic instability modes are basically large-scale structures.
Yes.
They must be influencing turbulence here, and there should be some turbulence interaction here, which is again in turn going into molecular scale, and it's not molecular scale to smaller scale, and augmenting the flame propagation. So if you can show some and share some more insights on that.
Yeah, so you are absolutely right. So what we looked at is basically the coherent structures, okay, the large scale coherent structures, because the major disruption happens at that scale. Of course, the turbulence, as you rightly said, it will enhance mixing. It will also change how the droplets are actually organized. So actually, the study that I did not show is basically we did one other thing. We actually injected droplets at particular regions of this particular flow field. So instead of a spray, what we decided, because the spray has this primary atomization, and then you have secondary atomization and all this crazy stuff. So why not actually inject droplets of a particular size at certain regions of the flow field, that is at the shear layer, at the vortex breakdown bubble, and see how it automatically heterogenizes. So in fact, we found that if we inject droplets, monodispersed droplets of a particular size, it automatically depending on where it is injected and depending on the phase of these coherent structures, it automatically gets reorganized into several Stokes number limits. And so you get certain, larger droplets on a certain scale and smaller droplets on some other scale. So what happens is that no matter what you do to the spray, even if we talk about the sprays have to be very fine, very homogeneous, very monodispersed, ideally that is what you want from your spray injector, it does not, the flow is so complicated. And as you rightly said, it is due to the coherent structures largely, which does the crude filtering. That means if you imagine it's like a wheel that's so some droplets will be ejected on one side, some droplets will be ejected to the other side. And then you have the turbulence, which then acts on them and basically leads to phenomena like coalescence, small scale coalescence, okay, small scale dispersion, okay, and so all these things naturally happen. So there is no way that you can control the outcome. What, however, you can control is that if you study enough amount of statistics of this particular problems, perhaps you can give a good idea, okay, if you inject droplets in the shear layer, perhaps this will be the scale structures, right? Now, your other question that on the hydrodynamic part, that how the hydrodynamic topology and the flame is actually can be attacked mathematically. Now, one way of doing this is that what people have done, well, the literature is abnormally thin on this on the other side. Okay, so, and obviously there are no closed form solution, there is nothing. But what we can do predict, like people have done in the case of blood body stabilized flame also, that if you, but the blood body is a little bit easier because you know the vorticity dynamics quite well.
Right.
Because you know the barometric torque that are generated,
Right.
get some understanding. But in swirl stabilized flow, the flow physics, because of these hydrodynamic transitions, which is not present in the bluff body, is abnormally complicated to begin with. I have not seen a paper which gives a full-fledged understanding of the swirling flow. So, for example, people cannot predict the conical breakdown at all. Okay, so we can hypothesize certain things, we can propose certain mechanisms, but there is no criteria or no mathematical basis by which one can say, okay, this is going to happen. So it is after the fact. We are doing post-mortem, like this is what may have led to that. So, but I would imagine if we can write a vorticity transport expression for the swirling flow, okay, and then couple it with the flame dynamics, perhaps we would be able to give an idea that how this stretching happens, how the flame extinction phenomena happens. But I have not seen a whole lot of paper on this. I'm not considering the numerical work in this particular thing because that will be like experiments. You do numerics, it will be like experiments. But what I think you are looking at is some kind of a physical space. Like in love body, there exists some that
exactly similar things.
Yeah, but I have not seen that over here because of the complexity of, I guess, of the flow field. The flow field is largely very much more complicated than a love body stabilized flame or a wedge stabilized flame. Okay, it's much more complicated than that. So more effort will be required, I would say. So, hope you do it.
It's an interesting problem.
I think Tim was doing something like this, okay, when he talked with me, maybe a year or so back, but I don't know where it has gone. I have not seen anything concrete as such in the literature.
Okay. Yeah, I think almost we are at the end of the scheduled duration. Anybody else? If you have some comment or question, we can take one question. Okay.
Yeah, just a small query to Professor Basu. Yeah, so this face mask experiment, whenever you have done, so have you thought of giving some droplet which is having slimy mucus kind of thing also?
Yes.
In
Yes.
because top will be having slimy mucus also, which is semi-solid.
Absolutely.
So,
actually, the sessile droplet that I showed some results that has actually got mucin in it. So we added mucin at a particular concentration just to mimic the the mucus portion that is coming out, right? So we have not done it in the case of a face mask, but that is something that is going on right now as I speak. So yeah, of course, the viscosity will be higher. So I would say the atomization will come down a little bit. The penetration might be a little different, but I can share once we have the data.
So maybe we can use single layer mask and go for panel hopping at Kolkata.
Yeah, I guess single layer may not actually save anybody.
But Professor Basu only tells us that what happens if the COVID infected person, which type of mask he should use. But for a common person, for his own protection, which type of mask he should use?
I think first, I think better not get out of the house. Probably that is the case to do. But if hopping has to be done, I think 3-layer should be okay. Would be kind of okay. N95 N95 is hard to get. There are a lot of fake N95. So I think 3-layer cloth mask, even cloth mask we have tested, that is okay. I mean, of course, if you stay in the proximity, the main problem is that if you stay in proximity with a particular person, say for hours, what happens is that even though these masks protect most of the droplets, but there will be a few droplets that will come out. There is a statistical. So more you stay, more is your inhalation probability. And because it is infectious, more is your chance of getting infected. So that's what people want to have. I mean, if you go out, don't stay in one pandal or maybe don't stay around.
So if you increase frequency of interaction rather the duration of interaction, in case you have to stay longer, you make it in more sets rather than a longer interaction.
Right. Absolutely. Absolutely. That is how this is going to happen.
Okay.
That's great. That's great. Yeah. But it's better to stay at home as much as you can.
Yeah, better to make it zero.
Better to
At least epsilon.
Yeah. Actually, yeah. True.
Thank you, Professor Basu and Professor Roy.
Thanks.
I think formal thank you will be coming from the organizers.
Yeah. If there is no other question, I'll ask Professor Nayak to take over the stage.
Yeah, one question actually somebody asked here also. So nice lecture, sir. Will you enlighten about some tumor treatment related to heat and mass transfer application?
So that is something that I have never done because nothing on the fundamental. But tumor treatment, heat and mass transfer, there will be people. Okay, I mean, I don't want to comment on something in which I have not much of an idea. Like tumor would be. I am talking. I think you are talking about either if it is radiation treatment. Okay, there will be more qualified people than me to talk about radiation transfer. But if you are talking about if it is a drug-related thing, that means it is controlled release. I believe that the tumor secretes some kind of a chemical and the drug has got a matching chemical, and so they bind with each other, and then I think that is the question probably. Yeah. So that's what I see in the chat window. So it is exactly so. In those kind of things, I think your surface modification becomes very important. That means when you interface, that means you clothe the drug in some kind of a chemical shell, very much like the virus does. It's exactly like the virus, right? So it has a chemical shell with a particular signature, right? So the tumors needs to have something complementary in which the drug can bind with it, and therefore it can actually destroy it. But to find out those signatures, those matching signatures, that is what I think called targeted drug delivery these days. That's how you actually have tailored nanoparticles infusing. You put the drug in a nanoparticle coated shell of some kind, right? And then you kind of transport it near the tumor, where the tumor molecules can actually mate with these nanoparticles. So I think there are a lot of work that is being done in IISc itself in the nanoscience department. I think I can direct you to Professor Ambarish Ghosh's research. I think he does something on nanorobots, which can carry the drug to a targeted tumor cell and then can actually destroy it. Obviously, these things are still in its infancy, I should say. It's not that it is like a qualified method of treatment, but I think there is a lot of progress that has been made in that particular area. So I don't work in that, but I can, as I said, you can talk with Professor Ambarish Ghosh or read his papers. I think recently had a paper somewhere. I forget the name of the journal. So you can read it and perhaps get an idea. But basically, it should be something like that. Okay. I think there is one more question. Can you explain again the sessile droplet distribution? So sessile droplet distribution, by that I mean that it is the array of droplets that you are talking about. So array of droplets in this particular case, that is depending on your application. For example, if you do 3D printing, you will have a lot of droplets sitting side by side for a while, right? And then you might have these arrays of droplets which are drying in, say, biomedical applications. Okay. You're trying to do some kind of a DNA isolation. There can be varieties of applications. So these droplets can be only in two ways it can be arranged. Either it can be arranged in a linear array or it can be arranged in a two-dimensional array, right? I mean, that's the two arrays that I can think of. So depending on what their arrangement is, you can cast the equation accordingly and you can predict that what will be the evaporation time, that is the drying time in this particular case, depending on the proximity of the droplets. I think that is how the droplet sessile distribution should work. But however, you can read the papers also that are there that we have in a varieties of journals. So you can read that and get an idea. Exactly the math part I did not elaborate, but you can get an idea on that how.
Okay, thank you, Professor Boshu. It is really wonderful to hear from you and for this informative talk.
Thank you so much.
Yeah, we are really thankful for your giving your valuable time. And on behalf of organizing committee, I am thankful to Professor Boshu and Professor Somnath. who has spared their valuable time to moderate the session and deliver the lecture. So thank you all. Yeah. So
you so much.
maybe physically we can just meet some other time.
Sure. Once the COVID is over. Thank you so much. Thank you everybody for listening to me. If you have any questions, feel free to write to me also. I'm available. So I will try to answer whatever questions that I can. Thank you so much.
Okay. Thanks all the participants to attend this session, and next session will be from Ian Griffiths, and he will speak on how math scans have evolved, a popular talk. So the talk will start at 3 p.m. So just try to join. Thanks to all once again, and we can just stop this meeting now, and I'm just requesting to quit.
Thank you.